A conveyor gear motor can match the required power on paper and still fail in operation. Loaded starts, incline travel, material surges, frequent cycling, restricted airflow, or an incompatible shaft interface can expose weaknesses that a simple catalog comparison will not reveal. Reliable sizing begins at the driven machine. Define the conveyed mass, required throughput, belt or screw speed, incline, friction, acceleration time, operating hours, stop frequency, and consequences of an unexpected trip. The required output speed must be tied to the pulley, sprocket, or screw. Selecting a familiar reduction ratio is not enough if the resulting shaft speed causes material slip, unstable flow, or difficult mechanical adjustment. For an existing installation, verify actual shaft speed, rotation direction, pulley dimensions, and gearbox markings. Previous retrofits may have left nameplates and model references inconsistent with the machine's current configuration. A mechanically interchangeable replacement can still be functionally wrong if its ratio or rotation does not match the process. Torque must then be separated into continuous and peak demand. Continuous torque represents stable operation. Peak torque covers acceleration, loaded starts, material surges, blockage release, reversing, and process upsets. The gearbox experiences this complete load history, not merely the average motor power. Calculations should identify where every load assumption came from and whether the available margin covers normal wear, belt misalignment, loaded rollers, lubrication condition, or changing material moisture. Service factor provides structured margin for the severity of the application, but it should never be treated as a universal uplift. Its selection depends on load variation, operating hours, starts per hour, shock, ambient conditions, and maintenance expectations. Recording the chosen factor and its basis allows procurement, engineering, and maintenance teams to understand why the selected rating exceeds the calculated running torque. Thermal capacity requires a separate review. A reducer may transmit the required torque yet accumulate excessive heat during extended operation. Mounting direction, housing location, ventilation, lubricant quantity, ambient temperature, and start frequency all influence the result. Variable frequency operation adds another consideration because prolonged low-speed running can affect motor cooling. Supplier thermal ratings should therefore be checked against the installed duty rather than accepted as generic catalog values. Inclined conveyors demand particular attention. Gravity can increase starting torque and create rollback risk, making a brake, backstop, or controlled starting sequence necessary. Frequent loaded starts can impose greater mechanical and thermal stress than continuous running at the same average throughput. Reversing conveyors and mixers introduce similar transient loads, especially when sticky material, batch variation, or changing viscosity raises breakaway torque above normal running torque. Installation limits can disqualify an otherwise suitable drive. Confirm the gearbox envelope, shaft protrusion, flange, mounting surfaces, motor position, guard clearance, lifting route, and access to lubrication and inspection points. Outdoor, dusty, humid, chemical, food processing, or washdown locations also require confirmation of sealing, vent arrangement, corrosion protection, lubricant grade, and ambient limits. The complete drivetrain must be reviewed together. Couplings, shaft alignment, brakes, backstops, controls, and the driven shaft can alter the torque transmitted during starts and stops. A stronger reducer will not compensate for an unsuitable coupling or poor starting sequence. Before approval, document the required shaft speed, continuous torque, peak torque, operating profile, service factor, thermal conditions, mounting position, shaft and flange dimensions, motor data, rotation, lubrication requirements, and maintenance access. Support the decision with measured machine data, arrangement drawings, supplier ratings, and verified documentation. This disciplined process turns gear motor selection from a power rating shortcut into a defensible engineering decision.